Hi everyone, I am back in my office here and I'm going to redo this problem from class today so I can spend a little bit more time setting up the math so that we're clear on how we were solving this one here. So we're told here that copper has two natural occurring isotopes, the predominant one being copper 63, we're told, with its atomic mass given, and the abundance of 69.150%. The abundance and the fact that there's only two isotopes tells us that the other isotope, let's call it isotope 2, that isotope 2 would have a abundance of 100% minus the fraction that's the copper 63, so that's going to leave behind 30.850%. That'll come into play in a minute. So then let's also try to see what we're being asked here. What is the mass of the other natural occurring isotope? So we want to know the atomic weight of the other isotope that naturally occurs for copper. And so for any element, we can write its average atomic weight would be equal to the sum over all natural occurring isotopes, the sum of the fraction of a given isotope times the atomic weight of that isotope. And so if we do this for copper, we can look up copper's average atomic weight is 63.546 AMU. Now where did I get this number from? I get this number here from the periodic table. So I get that number from the periodic table. It's the average atomic weight for copper. And then that's going to equal the fraction that's the lighter isotope. So that's 0.69150. I'm just writing the percentage as a fraction. So I'm just writing this percentage here as its fraction without the 100%, and then times the atomic weight of that isotope, 62.9296 atomic mass units. Then I'm going to add, because this is a summation, so I add the abundance of the other isotope, and then times the atomic weight of isotope 2. And this atomic weight here is what we're looking for, so this is our unknown. And so then algebraically, we're just going to try to solve this expression. So I'm going to do that in a couple steps. I'm going to do this arithmetic here. So if I do the 0.69150 times 62.9296, that's going to be equal to 43.5158. Throw in another digit, let's go to one extra digit of AMU, that's going to be equal to 63.546 AMU. Then I'm going to add the, keep the 0.30850 times the atomic weight of isotope 2. And so then I'm going to subtract 43.5182 from both sides. So I subtract that from both sides. So I do 63.546 minus 43.51582 gives me 20.0302. That's going to equal 0.30850 times the atomic weight of that second isotope. And so now all I need to do is divide both sides by 30850. So I'm just dividing both sides by that number in front of AW2. So then my AW2, just running an arrow in here, so my AW2 comes out to be equal to 64.928. So there you go. That's how we find that atomic weight of the second isotope. And then the second question here is identifying the mass number and the atomic number of the isotope. And so this is close to 65 AMU. And so my mass number is going to be 65 atomic mass units. You can certainly notice that the first isotopic mass was copper 63, close to 63, a little bit less. And so this is going to be copper 65, so that's my mass number. Then the atomic number for copper is on the periodic table. So you look the atomic number up on the periodic table, it's the atomic number, it's 29. And so you can see the difference between these two isotopes is copper 65 has 2 more neutrons than copper 63. And so that's how we can work out the math on this one. So we can do some math problems with isotopes and average atomic weights, but some of the key details are: 1, know how to use a periodic table to get your average, know how to do the summation, so know how just to take a fraction times the atomic weight and sum those up for all possible. You know, in terms of solving an algebraic expression, we usually limit it to isotopes that are, you know, where there's 2 isotopes for a given element, because once you get into 3 or 4 or more, it gets really complicated with the math. So with these math problems, we usually like to keep it to elements that exist as 2 natural occurring isotopes. If we give you an example, like sometimes we could give you an example where an element has, like, let's say 4 different natural occurring isotopes. Well, one example could be if we give you each of those isotopic masses and each of their abundances, you can just simply do the summation math pretty easily to work out the average atomic weight. So that's maybe the range of possibilities, is doing math problems with algebra where we have 2 isotopes, maybe doing the summation when you have multiple isotopes, and just doing the summation if we give you each of the fractions and each of their atomic weights, and just doing the math to sum up to the average. And then the last thing is knowing to get the average. If you know, you might need to look that up in the periodic table.